Okay, hey folks, we are getting into some really cool stuff. Module 6 on the hydrogenic atoms. So we are finally going to take all of this stuff we've been learning and build it up to talking about real atoms. Super cool, exciting stuff. So in our first learning goal here, know the hydrogen atom total energy operator and being able to apply the separation of variables techniques to this system. Let's do it. So here is our picture, and we might notice that this looks strikingly similar to our particle on a ring model, because it is. And we're also going to allow this to pitch in and out of the theta dimension. So we're going to use a lot of the stuff that we got from the particle on a sphere model. So now you can see our Hamiltonian is going to be based on the following. The kinetic energy of the electron, which we can write as negative h bar squared over 2me, so that's the mass of the electron, times the Laplacian for the electron. We're going to have a kinetic energy of the proton, so that's also going to follow a similar pattern, negative h bar squared over 2 now mp plus for the mass of the proton, and then the Laplacian for the proton system, plus this potential energy operator. And now we can finally consider the charges of these two objects using the Coulomb potential between the two. So the Coulomb potential describes the interaction between a positive point charge and a negative point charge. So here, describing all of the elements, capital Z is the nuclear charge. So, and in the case of the hydrogen atom, it's just +1. E is our fundamental charge. So that's the value 1.602 times 10 to the minus 19 Coulomb. The radius is our electron distance from the nucleus, so we can see right there. And this epsilon is known as our vacuum permittivity. So vacuum permittivity. And that has a value of 8.854 times 10 to the minus 12 Coulomb squared per joule meter. So now we can add that in our hydrogen atom energy operator, negative ZE squared all over 4 pi epsilon r. Well, as it turns out, this would be quite a heavy lift. I mean, it's already going to be complicated, but by including this kinetic energy term of the proton, it's going to make this even more complicated. So the standard process now is to combine these into this common term by creating a common coordinate system. So our common coordinate system will be 0, 0, 0. So the origin for the position of the proton. And then we can also consider the reduced mass between those two pairs as me times mp over me plus mp. So that allows us to combine this into one term, which will be negative h bar squared over 2 mu times our Laplacian of this particle on a sphere system, where the origin is the position of our proton. Okay, so that is our operator. So you know what's coming next, right? Cry, pray, guess, solve. Let's do it. So here is what we know. We have our Hamiltonian for our electron. We have our definition of the Laplacian. I want to note that this is just a slightly different version of the one that we showed. And I don't want us to get us too concerned with those details. This version of the Laplacian is perfectly well suited for solving this problem. And then, of course, we have the Legendron, right? We can't think about that thing. Or we can think about it, but maybe we don't want to because of how complicated it is. So now in our separation of variables, we're going to separate the radial components from the angular components. And for ease of notation, I'm just going to write that as psi times ry. And another thing that we can rely on, which we didn't go through this too heavily in the spherical harmonics section, but we will take advantage of this now. When the Legendre operates on the y function, we get the following eigenvalue and original function, where this YL-ML is the spherical harmonics that we derived. So this is going to be useful for us to simplify the math. Okay, let's put it together. So it's going to go negative h bar squared over 2 mu. And now I'm going to substitute in this version of the Laplacian, 1 over r times the second derivative in r of r, and then plus 1 over r squared times the Legendrin. And then now that operates on psi. So our psi is now ry, right? And then now we have our potential energy term, which is minus ze squared over 4 pi epsilon naught over r. And then that also operates on psi times ry. And now all of that equals E times psi, which in this case is ry. Okay, so now our procedure is going to be to distribute this through and to pull any derivatives out in front that we need not worry about. So I'm going to do that here in one step. So the first thing that I'm going to do is apply ry to this term over here. And I'm going to note that y will not depend on the second derivative in r. So we can bring that out to the front of the expression. So that's going to go as the following. Negative h bar squared over 2 mu times big Y over r. And now the second derivative of r squared r of r. Okay, so that was applying this term through to this term. Now we can push this other term through. And I'm going to write that as the following, because we recognize now the Legendrin is going to apply to ry, but the Legendrin only applies to our angular components. So we can do the same thing. I'm going to say r over r squared and the Legendrin squared, or the Legendrin operating on y. And then now we can just keep all of this other stuff the same. We didn't change any of that, equals ERY. So now I'm going to do a couple steps at once. For one, I'm going to push all of my constants through. And I realize now that I'm actually going to keep this in parentheses, because technically that negative h bar squared 2 mu, I should have distributed through to these other constants, right? But I can correct that by including those parentheses. So I'm going to push those constants through to the other side, and we'll go from there. So we'll have now that's y of y over r, second derivative in r, plus r over r squared, the Legendrin operating on y. And then now I need to apply those constants here to this system. So that's going to be a negative times a negative, which gives me a positive. I can see that I'm going to have a 2 mu ze squared on top. So that's going to go mu ze squared. And I've got a 2 right there, but you can also see that I've got a 4 right there. So I'm just going to, for now, leave this with the 2 and the 4, and you'll see why I'm going to leave it there for the time being. So then I will have a, let's see here. Oh, I lost my place. So yes, it's going to be 4 pi epsilon r h bar squared. Okay, lovely. And that's times ry, and that equals e to the ry. Cool side note, the Bohr radius, a naught, is equal to 4 pi epsilon h bar squared all over mu e squared, which maybe we remember that that's 52.9 picometers. So we can see buried within all of these constants, we've got the Bohr radius. So that's kind of fun. Okay, so now I'm going to do, oops, and you know what? I forgot to apply the constant through to this side. So let's fix that really quick. So that's going to be -2 mu e over h bar squared times ry. And maybe we might notice that is our wave number solution k, which is also pretty cool. So we're getting some familiarity here. Okay, so now upon inspection here, I can see that I can do a couple of tricks. So first of all, we want to apply this through so that we can do that operation. And then when we do that operation, we can see it's going to give us back the wave function, right? So that's going to allow us to divide everything out by y. So let's go ahead and do that on the next slide. So we note that the Legendrin squared operating on y just gives us -L times L plus 1 times y. So let's put that result in here. So we're left with y over r times the second derivative in r of r minus, now we can put this chunk in, L times L plus 1 all over r squared times r times y. And my r was out in front before, but this is sufficient the way I've written it. And then now I'll write that as ze squared times mu over 2 pi epsilon r h bar squared. So I took care of the 2 over 4 times ry. And now all that equals -2 mu e divided by h bar squared times ry. So now hopefully I can see that I am able to eliminate y. I can't eliminate r because I have an operation here where I have to take the derivative or the second derivative in r. I'm also going to multiply everything by r to clean up this mess in front. So we're going to say divide by y multiply by r. So, and in doing that, I end up with the following. Oh, and then, sorry, one last other thing. To make life easier, we're also going to call, sorry, let's go ahead and do that one step at a time, 2 steps at a time. You know how things go. So second derivative in r of r, right? So we eliminated that term in front. And then now I'm going to write that as -L times L plus 1 over r squared. And you'll see in a moment why I'm going to not cancel these r's, but I'm going to call this r times y. And you might be able to see where this is going, hopefully. And then now I'm going to say that that's ze squared mu over 2 pi epsilon naught r h bar squared. And I'm going to keep it as r of r still and not cancel those r's. And then now this will all equal -2 mu e over h bar squared r times r. So hopefully what we notice, we've got the appearance of this r times r in all of our terms. So we're going to define a new function here just as a matter of convenience that says u of r equals r of r. And that's going to allow us to just replace this in a simple way. So finally what we end up with is the following. Second derivative of the function u of r minus L. Oops, and you know what? I meant to eliminate that y. Maybe you were thinking, why isn't that y gone? It is gone because we divided by y. There it is. Okay, so now that's L times L plus 1 over r squared times u of r plus all of those constants, ze squared over mu 2 pi epsilon r h bar squared times u of r, and all of that equals negative 2 mu e over h bar squared times u of r. Okay, goodness. So we are finally in a position to solve this thing. I know you might be thinking, what have we been doing this whole time? Well, this whole time we've just been working on the separation of variables. And what I want to note here is we have fully separated the functions in R from the functions in theta and phi. And it's worthwhile to note that we already solved those functions in theta and phi. So now in the next video, we will explore how to solve this radial function. I'll see you in the next video.